Now, are you
Yep,
seeing
you're
the right
good.
thing? All right, great. Okay, thank you, everybody. So I'm going to talk about analogy versus rules in cognitive architecture. I'm not using the title John suggested, which is Analogy Rules in Cognitive Architecture. That's very sweet, but I'm not quite there yet, although I'm heading that direction. So I'm trying to look at how reasoning ought to work in cognitive architecture. So in our companion cognitive architecture, we're more at the rational and social bands, as to harken back to John's recap of Newell's time thing. But the issues here are actually relevant to all of them, I think. And I'm going to tell you about the Continuum of Knowledge account that Deidre Gentner and I have been working out that actually takes a very different perspective on a lot of these issues. And then I'll show you how this works in two tasks, one common sense reasoning and the other natural language question answering. And I'll end by pointing out some useful resources that you might find helpful in your own cognitive architecture work. Okay, so rules. Rules are a wonderful thing because if you think about programs, you take a snip of a program, it's not a program, right? It's not a correct program. You take a snip of a production rule program, it is still a program. So that's one of the reasons why rules of various kinds are ubiquitous in cognitive architectures. So the classic is production rules as used in ACTAR and SOAR and many others, incremental learning of procedural knowledge, power law of learning, one of the interesting signature results that said, hey, there's something to this idea. Very cool stuff. Now, a lot of different architectures use things other than production rules. So Icarus, Arcadia, all have different sorts of rule systems, for example. But we're looking at a different question here. So the question is, to what extent can analogy replace rules in cognitive architecture? Now, we are not purists. So in companions, we also use Hornclaw's rules for backward chaining. We have HTN plans to implement high-level mental procedures. We have unit clause resolution operating in the working memory. Okay, but nevertheless, you have to ask the question, how far can you go in replacing rules with analogy? So if you think about how rules work, you've got, let's see if I can really get fancy here. Pen and laser pointer. Laser pointer, okay. So you've got this massive pool of stuff, right? And you have spreading activation for retrieval in many systems as a way of saying, of all these rules, which are the rules I should be using right now? And then you do pattern matching to apply them to elements in working memory, and you get more elements in working memory, and that's how the architecture turns over. And you've got learning mechanisms like chunking or inductive logic programming that produce new rules and add to that set. Okay, so that's the kind of stack for traditional rules at a cartoon 50,000 foot level view. Here's the equivalent level for using analogy. So now you've got a massive pool of knowledge that consists of rules and facts, but also cases. To filter these things, you use analogical retrieval, our MAC-FAC model, and applied, instead of pattern matching with logical variables or pattern variables, we use a structure mapping engine to apply these to things in working memory. Now, this working memory is organized into microtheories, which is basically a way of having multiple cases in there, psych-style microtheories, by the way. And now, of course, that is what makes our engine go around, and we have a system called SAGE, Sequential Analogical Generalization Engine, that incrementally produces probabilistic generalizations, relational descriptions, as examples are accumulated. So that's our sort of way of thinking about these things in the companion architecture. Now, psychologically, in fact, long before companions, Deidre and I were thinking that this is the way human knowledge works. So think about human knowledge. We have a vast set of experiences encoded by our perceptual system at first when we don't know anything else. And through a combination of learning on our own and cultural knowledge, we start re-encoding those things and we accumulate this knowledge over time. And analogical generalization gives us a mechanism of producing more and more abstract knowledge that gets increasingly portable and more applicable, with rules being a kind of insane limit case in applicability. But the intermediate points matter too. each and every one of these intermediate levels of representation can be used in reasoning and performance, even as they continue to be abstracted, because the pattern matching is done by analogy. There's no magic state necessarily where you turn it into a variable. Okay. Now, we've actually done a lot with this model. So we've used it to model conceptual change in physical domains, ranging from Scott Friedman's timber model, which starts all the way from raw experiences and goes up to causal mental models. We've done learning at the expert refinement stage, cross-domain analogical learning. I'm thinking of Matt Klink's PhD thesis, for example, and work that Tom Moyang and I did at looking at novice expert differences. So we actually have some evidence that this can work across a broad range of knowledge types and explain various phenomena in human conceptual change. Lately, we've been actually applying this to social reasoning. So the analogy is social reasoning and learning is like physical reasoning and learning. It's the same mechanisms, but more complex belief structures. So think of the bottom as things you've experienced as a social being, or if you're a piece of software, stories that you've read. We do a lot of natural language research. And these get abstracted away. The most solid piece of work here is Irina Rybkina's Analogical Theory of Mind. Irina is defending her thesis next month, and it's a very cool thesis. She's modeled several phenomena. She's actually now using this in work with Laura Hyatt, who you'll also hear from during this meeting, in doing reasoning about other agents in Minecraft. Taylor Olson, another of my students, is doing work on analogical learning of social norms from experiences. And we have a Friends of the Kiosk project where we're actually trying to build companions into something that can befriend undergraduates. We actually have an IRB protocol for befriending students, which I think is probably the first one anywhere. Now, let me show you two detailed examples. Well, okay, not that detailed given our timing constraints here. But the first is common sense reasoning. Common sense reasoning is viewed as one of the hardest problems in artificial intelligence. There's a lovely survey by Ernie Davis and Gary Marcus that appeared in CACM a few years ago. And if you think about it historically, there's been three approaches. Back in the days when non-monotonic logic roamed the earth, there were people who thought, we'll find exactly the right logical formalism, and that will do common sense. It's all about defaults, and with the right reasoning, that's all we need. Didn't work out so much because you need a lot of knowledge. Another approach is to accumulate massive numbers of logical axioms. That's the approach the Psych Project has taken, and in fact is still taking. They have, despite all the nasty things people say about them in the popular press, have a rather impressive knowledge base, a very impressive reasoning engine, and lots of deployed applications. So this stuff is scaled nicely, and it works for a lot of things. What's missing, in my view, is experiential knowledge. So Psych is a fantastic system of semantic memory, but it doesn't have pretty much any episodic memory. A third approach that people have been applying more recently is we're going to generate massive bodies of text and have the system mush those into something, into a nice distributed representation, and then we'll use those to answer questions. Okay, Comet is an example from that, from UW and AI2. The good thing about these systems is if you use them on multiple choice questions, you can get interesting answers. The bad news is if you look at the results in detail, they're often extremely noisy. And it's hard, since they're all based on words, it's hard to imagine a system actually using it as something to reason with in a constructive way, because you can't tell which are the right answers and which are the wrong answers. Now, our approach, if we were going to pick one of these, would be closest to the Psych approach, because in fact we use their ontology. But what we do is something different. So Dedry Gentner, with whom a lot of this work is done in collaboration, has argued that analogy is used throughout human reasoning and learning. And this includes common sense reasoning. And then what representations do common sense reasoning use? Well, qualitative representations. Best argument is in the book that just came out last year, which basically is making the argument that human beings in their conceptual structures for reasoning about continuous phenomena, both the physical domain and the social domain and aspects of their mental life, use qualitative representations. Qualitative representations provide a bridge between perception and cognition. Think about the kind of quantitative, qualitative model that John was talking about in SOAR's visual system. And they provide representations that are useful for common sense reasoning. Now let me show you an example. So there's a test called the Choice of Plausible Alternatives developed at USC, and it's got a question like this one. The baby pulled the mother's hair, what happens as a result? And they give you two answers. The mother grimaced, the baby burped. And you're supposed to pick one. Okay. So rather than have a ton of rules, we have analogies. The rapidity of common sense knowledge, we think, occurs because we're doing analogical retrieval, but not just one analogy. If it's just one analogy, then you're talking about having an even more ginormous knowledge base than I think we do. But if you can chain them together like rules, then analogical chaining lets you do rule-like reasoning, but without having gone all the way to rules, that intermediate level of knowledge. So here's a set of common sense units. Think of these as little tiny cases. Predicate calculus, there's an event, maybe two events, and relationships involving those. So I've glossed them in English here. Hair pulling causes pain, pain causes grimacing. And so you get the question automatically encoded by our natural language system and companions. And it retrieves first the hair pulling causes pain, so it infers the mother is hurt. Pain causes grimacing, so it infers the mother grimaces. That answer matches its understanding of one of the answers, so it stops and says, that's the answer. Okay. So now let's think about this as compared to rules. So like rules, these common sense units, chaining over them, supports prediction and explanation. You can justify conclusions because you can trace back through the inferences that SME makes, and you can flexibly construct complex arguments by chaining. Now, if you're a psych person or someone who loves deductive rules, say answer set programming or any other logical system, you are a little tense at this point because these operate by partial matching. It's quite happy to postulate things that don't exist. They don't require a complete or correct domain theory, which if you're going to do logical deduction, you really would like. And there's no guarantee of the accuracy of the results. Now, I think that's just life. I mean, when you talk about broad reasoning and experience, you're not going to get something that's a fully deductive theory. Lots of reasons for that. The great thing about common sense units is you can use what we call microstories to supply them interactively. So there's either 1 to 3 sentences in simplified English that are automatically translated to predicate calculus. And it's a lot easier to construct common sense units by natural language understanding than to try to construct complete and correct logical rules by natural language understanding. If you ever tried to do that, you know how hard that is. So how well does it work? Well, the reasoning process is we forward chain analogically from the understanding of the initial statement of the problem, and it halts when one of the alternatives is inferred. And if both are inferred, it prefers the alternative with fewer steps. So we start with the COPA exam, and we automatically encoded 15 questions out of 500. Why only 15? Because at the time, we have very limited language resources, and we're going to be coming back to that. There's all sorts of interesting linguistic phenomena in this test, like wild language in general. And we're happy to say that it solved 14 out of 15 questions correctly. That's the good news. Now, of course, there's limitations. So, for example, even with a small common sense library, you can have reasoning wander. So here's an example question. A motorcycle crashes on a bridge. A, the motorcyclist dies, or B, the bridge collapses. Now, the system had a lovely hypothesis. Maybe it collided with an airplane, and that's what caused the motorcycle to crash. Great if you're an episode of Fast and Furious, not so much common sense. So it needs to learn what analogies are reasonable when, and I think that points to the need for more testing of the accuracy and plausibility of these analogical inferences. Okay, So that's task 1. Task 2 is a natural language task, and there's 2 approaches to natural language understanding these days. Machine learning is not just magic. There's hand engineering of massive data sets. There's hand engineering of hyperparameter search. At Google, the joke is this is graduate student descent. You get impressive results on multiple choice tasks, but as the EMLP 2018 paper and others have shown, these things are actually very brittle. By contrast, high precision understanding, which is what we're doing, where you construct conceptual structures that are intended to be human-like, use hand-engineered massive knowledge base, hand-engineered grammar and algorithms. We get impressive results on questions where you have to generate the answers, but currently hard to scale. And so we're trying to tackle scale, they're trying to tackle accuracy. So the approach we've come up with is called analogical training. Surprise, surprise. So the companion's language system is very general. We've used it in learning by reading, in moral decision problems, taking a psychological experiment and turning it into something the system can use, learning from advice and strategy games. But what we want is a way to automatically adapt it to new domains without annotated data, because humans do not get data annotated in their internal representations. Cognitive science would be simple if it were, and with high data efficiency. So here's how that works. You give it question-answer pairs in English. The language system operates on those to give possible interpretations. A connection graph is constructed between those two things, and from that is generated a set of query cases that can be applied by analogy to interpret novel questions. I'm going to show you how this works on Geoquery, a really classic machine learning question answering task. So, training question. Which capitals are in states that border Texas? Well, capital could mean money, or it could be geopolitical capital. State could be state of matter, solid, liquid, gas, etc. Okay, but the interpretations of capital and states that allow you to construct a query that would give you the answers you're given are not the ones that involve states of matter or money, okay? Similarly here, a second training question, what rivers are in Utah? The Colorado, that could be a state as well as a river, green, color, San Juan, could be a city as well as a river, okay? So there's still lots of ambiguity, but again, the things that make those 3 answers come back with the interpretation you get constrains everything. Now, with just those 2 training examples, 2, not 200, not 2,000, not 2 million, you can already answer what rivers flow through states that Alabama borders, and what are the cities and states through which the Mississippi flows, and what are the cities and states that border states through which the Mississippi flows. Okay, it's compositional. It's the way human conceptual structure is. So in terms of data efficiency, systems that do this task tend to require about 600 training examples. Now, because these results we get are explainable, we can look at the results of an analogical train system and automatically construct an optimal training sequence. When you do that, we get comparable performance with only 50 examples. You notice that after only 10, we're already almost at 60% accuracy. And so this is a very data efficient way to learn. If you ever come by Northwestern, you can interact with our kiosk. It'll be nice to go back there someday. It interacts with visitors using speech and vision. It's got a companion running this full natural language stack under the hood. It's been in daily use since fall 2018. To train the kiosk takes 11 question answer pairs on average per question type, and the training takes a whole 5 minutes to run on a tablet. So again, very, very data efficient. Okay, so I've been arguing for a continuum view of knowledge with experience at one end, rules at another end, with analogical generalization incrementally building more abstract knowledge. But everywhere along the way, analogical retrieval and matching can apply this knowledge to new situations. And I've shown you that this sort of account can work from 2 very different tasks, common sense reasoning and learning to answer questions. Now, still many open questions about how to generalize this, how broad does it go? There's another one, which is a sort of different twist. So is there ever a transition to traditional rules with logical or pattern variables? We have done this in some of our experiments on learning causal models, turned them into traditional model fragments from qualitative reasoning, for example, abstractions that were learned from experience, okay, using information gain to make that switch. If you think about the properties of encoding, that might be something where you really do have something that's much more like, for instance, SOAR elaboration rules. Could you use a SOAR-like compilation process in combination with the sort of analogical generalization we do to make that transition happen more fluently? I think it's an interesting open question. I want to end with saying, look, we think there's a lot of value in analogy. And so the structure mapping engine has been publicly available for a while now. You can download the Common Lisp source code or a binary that lets you fiddle with it if you're allergic to Common Lisp. It's got a large set of benchmarks if you want to build your own implementation. And if you can build SME, then building MacFac and Sage are pretty straightforward. But they require a bet on what your long-term memories look like, which is why we don't bundle that up yet. And the second thing is our NextKB knowledge base. The ontology is distilled from OpenPsych, full microtheory support. We've got links to FrameNet for semantic translations, and we're always expanding those. Large English lexicon. It's got support for visual reasoning, spatial reasoning, qualitative reasoning more broadly. There's text files for using this with your own reasoning engine. We've also got executables that run it directly with our reasoning engine. And both of these resources are Creative Commons attribution only. We'd really love help in expanding NextKB into a really broad scale knowledge base. One of our big goals is to use companions to automatically bulk it out to where, I mean, we already have language coverage that's equivalent to research psych in our own open license resources now. We'd like to make the coverage of reasoning be as broad or broader than psych proper and have all that be open license. Thank you for listening.
All right. Well, we have a couple of questions. JFL asks, do you believe your analogy-based approach gives a principled explanation of how episodic memory becomes semantic memory in an architecture like SOAR?
Yes, I think it could be used to do that. And the trick is, so you know, the thing I think is really interesting is if you use MacFac as your sole retrieval mechanism, then where do you do the encoding to prime the pump? That's where I think a function for rules, even in the hardest core analogical account you can think of. I think that would still be a useful thing to do. And so if you think of as you do analogical generalization, it gets more and more abstract. And so at some point you've got no episodic information in there, right? So if you've got a separate memory you're storing those things in, then at some point you have the decision to make of, now this thing is so abstract it's going to fall out of the episodic memory into the semantic memory. So that's an interesting question.
Thank you. From Paul Bello, what's the relationship between the most concrete rules in your hierarchy and sense data?
We think they are sense data. That is, if you think about the way we do learning from sketches, those sketches are using qualitative relational representations that we think are what human beings are encoding in high-level vision. So Andrew Lovett's work on visual problem solving, for example, has demonstrated that those relational representations can be used to explain, Raven's progressive matrices, geometric analogies, visual oddity task. And so those are constructed. In fact, so we did PowerPoint there. One of my students now is actually using hardcore vision systems like edge finders, deep learning modules for doing object detection and boundary detection, and using those as inputs to CogSketch. Because we've always called it a model of high-level visual perception, and by God, we're running with that. Okay, we don't do the sort of focus of attention that Arcadia does. So the idea of having a whole scene there, if we give CogSketch a whole scene, it kind of goes, oh, far out, man, and computes all these visual relationships. You really want attention if you're going to deal with serious visual scenes.
Well, that's all the questions, but I'd like to give an exclamation from the chat. Finally, a view of common sense that I can get behind.
Well, thank you, James. Really appreciate that. And yes, Common Lisp does live.
All right, well, unless there are further questions, we will delay until 11, which Eastern time, which is the start of the next talk.
All right, hate to end early, but hey, better that than late. If anyone has any other questions or comments. Ricardo, question. Go for it. Okay, how do you perform corrective actions or deal with misinformation? That's a damn fine question. So in an earlier project, we had the learning by reading system called Learning Reader. And it would make errors, and they're very interesting errors. So for instance, the Jordan River enters the Dead Sea. And its interpretation was that there's an event of entering a container, and the container is the musical group, the Grateful Dead. That's not a misconception that a knowledge poor system is ever going to come up with. So with analogical generalization, you can actually get a notion of surprise. So you get something where you've got enough experience to where you think you understand the phenomena, and you get something that should retrieve something and it doesn't. And that's a case where you can go, whoa, okay. Now here's the problem. It could be that that's just a new part of the distribution. It's a new kind of thing you haven't seen before. Or it could be that you have an encoding error, okay? And telling those two apart is something that locally I don't know that you can do. There's a reason why human beings, when they're learning in a culture, do not just sit in a room and read books, right? They talk to people. They talk to people, they go experiment, and reasoning is the thing, putting the knowledge to work. That's the thing that helps you correct. That's the thing that helps you detect misinformation. It can't all be internal.
All right, we have time for one more. So let's address Ricardo. Do you think you might consider a rule, a case of analogical reasoning, a special kind of analogical reasoning, a subtype?
So in fact, that is on alternate Thursdays exactly what I think. That you don't actually need a separate mechanism. So if you look at unification and structure mapping, neither subsumes the other. Okay, so unification, you can have multiple variables binding to the same value, which would violate the one-to-one constraint of structure mapping. In structure mapping, I can map constants to other constants, which unification can't do. So there are some fundamental differences. You can construct a rule interpreter using nothing but analogical matching, but the rules are going to look a little different. Not too different, but a little different because of that one-to-one constraint. Is that what we're doing in our heads? I don't know. Open question.
All right, well, thank you very much.